Good afternoon, everyone. Welcome to the RSG Scientific Symposium. My name is Dongxu Huang. I'm a rising second year from the Department of Material Science and Engineering. So when people usually ask what I do for my research, well, a short answer would be I'm building electronics. But the real version, however, is that I'm using computational material science to understand hybrid materials that would be used to build our future electronics. So you might say then why does my research even matter to us as general customers? Well, this is the point I'm trying to make today. And hopefully by the end of this presentation, we could all see clearly this connection, and plus why my research is quite interesting. So to make this connection, I would first like to introduce what I mean by future electronics and what is hybrid materials. So when you look around at the electronics you have every day, the cell phone, the tablets, the laptops, they all come in different shapes and sizes, and they are used for very different purposes. But they have something in common, that is they are made out of materials that are rigid, hard, and they are made usually into regular shapes, such as a box. But if you go to a Walmart or go to Best Buy today, you might find some of these electronic devices. They do not look like what I just tell you. And these electronic devices are what I mean by our future electronics. And that is what my research ultimately targeted on. Also, even better, if you log on some of the research websites, you'll find some electronic devices that are so flexible, so soft, that they can be wrapped around and put into a human vessel. So what makes these electronics different? What allows them to be different? Well, that is they use a different type of material. So traditionally, electronics are made out of organic materials, by which I mean metals and semiconductors. These materials have very good electronic properties and mechanical stability. That's the reason they became the candidates for the modern electronic industry. However, it is the same characteristics makes them incompatible to meet the demands of our new electronics, that is flexibility or biocompatibility. To address this problem, we have to bring a new material. We have to bring organic materials together with inorganic materials. Then we will have the hybrid materials. And hopefully with this hybrid material, we could make electronics that has both the good electronic properties and the functionalities, and also all these features such as flexibility, biocompatibility, and cheap price that will lead us to the better electronics. However, there is a big challenge in the way we bring the hybrid materials to the actual electronic device. That is, we do not quite understand how inorganics and organics comes together. So these two materials have very different properties, and we have to understand in order to use them, how they can be put together, how they can function together, and how they could stay together. So to do that, what people usually do is they do experiments. They make a device, they make a prototype, they bring it under test for characterization, and then they find out the problem. They make a guess, or they make some improvements, they go through this research cycle again. Well, if we are dealing with the hybrid materials, we have a problem right in the characterization steps. Why is that? In short version, organic materials and inorganic materials are very different. They are almost on different length scales. They have very different chemical compositions, and they have a lot of difference in physical properties. So when you put a hybrid material under a microscope, what you really find is you cannot look at both compartments at the same time. That's almost like you are trying to look at an object with a microscope and a telescope from the same standing point at the same time. We just cannot find the right resolution. And this is where my research, this is where computational material science comes in to help. So instead of using experimental characterization skills, we use computers with a combination of our scientific understanding and computational modeling. We reproduce the experimental prototype in a term of a computational model, and we analyze upon that. Or we could view computational material science as a scientific version of Minecraft. Instead of building a McDonald's or building a castle, while building an electronic device. So I'm going to show you a little bit how this actually works. So this little yellow guy would be me with my laptop. I build a pile of inorganic building blocks and a pile of organic building blocks. I put them together in a way that they will look like an actual electronic device. In this case, it's organic molecules stacked in between inorganic sheets. And then I put this system into a simulation box that is equipped with chemical and physical rules that we input to guide the molecule, guide the atoms interact with each other. And we'll set up the temperature, set up the pressure, and we just allow it to evolve by itself. So these molecules, these atoms, will evolve by themselves as it is in nature. And in the end, we will have a final structure that we could not otherwise look with experiments. And also, we would have all the details of every single step, how the system comes from the configuration on the right to the left. We would find out how the interaction forces, how the potentials, and where all these atoms, all these molecules are in the space at every single step. So this is how computational material science could be related, could help the development of electronic devices. In summary, so with all the extreme details provided by computational material science, we could answer much better of how hybrid materials behave, how they interact, and with that scientific understanding, together with other scientists and engineers, we could deliver the next generation electronics that are much better, much cheaper, and with all the functionalities we could ever imagine. Thank you.